Far out in one of the spiral arms of the vast Milky Way, long before the Earth existed, long before the planets formed, there was only a quiet cloud drifting slowly through space. This cloud was enormous. Stretching across dozens of light years, it contained gas and dust left behind by older generations of stars. These ancient stars had lived their lives billions of years earlier, forging heavy elements deep within their fiery cores. When they reached the ends of their lives, some exploded in powerful stellar explosions known as supernova. Those explosions scattered their material across the galaxy. Carbon, oxygen, silicon, iron. These elements drifted through space and eventually became part of the giant cloud that would one day give birth to our solar system. At the time, however, the cloud was calm and silent. It floated gently through the galaxy, slowly rotating and gradually evolving under the influence of gravity. Inside the cloud were regions where the gas was slightly denser than elsewhere. These regions were colder and darker, hidden from the bright glow of nearby stars. Astronomers today call such structures molecular clouds. Inside them, new stars are often born. For millions of years, nothing dramatic happened in this particular region of the galaxy. The cloud simply drifted along its orbit around the galactic center. But space is rarely completely quiet. Somewhere nearby, a massive star reached the end of its life. When that star exploded as a supernova, it sent a powerful shockwave racing through the surrounding region of space. The expanding shell of gas slammed into nearby clouds, compressing them as it passed. When that shockwave reached our quiet molecular cloud, something began to change. The gentle balance between gravity and internal pressure inside the cloud was disturbed. Gravity began to win. The cloud slowly started collapsing inward. This collapse did not happen all at once. Instead, it began in many different regions throughout the cloud, where slightly denser pockets of gas started pulling more material toward themselves. Over time, these dense regions grew heavier and hotter. Gas flowed inward, dust particles moved closer together, and very slowly, the enormous cloud began transforming into something new. At the center of one collapsing region, matter accumulated faster than anywhere else. This region would eventually become the heart of our solar system. But at the time, it was simply a dense knot of gas surrounded by swirling material. As gravity continued pulling the cloud inward, something important happened. The entire system began to spin faster. This happens because of a physical rule known as the conservation of angular momentum. Just as a spinning ice skater rotates faster when pulling their arms inward, the collapsing cloud spun faster as its radius shrank. The once slow rotation of the cloud gradually accelerated. Gas and dust began forming a flattened disk around the central region. This disk would eventually become the birthplace of planets. At the center of the disk, pressure and temperature rose higher and higher. The growing core continued pulling in more matter, becoming denser with every passing 1,000 years. Deep within that forming core, the temperature climbed into the millions of degrees. Hydrogen atoms began moving faster and faster. Eventually, they began colliding with enough energy to overcome their natural electrical repulsion. And when that happened, something extraordinary occurred. Hydrogen atoms fused together. They formed helium. In the process, they released enormous amounts of energy. This process is called nuclear fusion. It is the same process that powers stars throughout the universe. And when fusion ignited in the center of the collapsing cloud, a new star was born. That star became our sun. At that moment, the solar system truly began. The newborn sun blazed to life, flooding the surrounding disk with light and heat. Radiation pushed away some of the lighter gases near the center, while leaving heavier dust particles behind. The sun contained almost all of the mass of the system, more than 99% of it. But the remaining fraction of material in the disk still held enough matter to create something extraordinary. Planets, moons, asteroids, comets. Entire worlds would eventually form from this swirling disk of dust and ice. But that process would take millions of years. For now, the young sun shone brightly at the center of a chaotic disk of gas and dust, illuminating the birthplace of future planets. Tiny particles within the disk began colliding with one another. Some stuck together, others bounced apart. Slowly, almost imperceptibly, grains of dust began forming larger clumps. Pebbles formed, then rocks, then objects kilometers across. These early building blocks of planets are known as planetesimals, and their story was only just beginning, because the early solar system was not a calm place. It was a violent, chaotic environment filled with collisions, explosions, and growing worlds constantly reshaping one another. From this chaos would eventually emerge the familiar planets we know today: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. But those worlds had not yet taken shape. The disk was still young, the building blocks were still forming, and the story of the solar system had only just begun. In the earliest days after the birth of the sun, the young star shone within a vast, swirling disk of gas and dust. This structure, known to astronomers as a protoplanetary disk, stretched for billions of kilometers in every direction. If we could have looked at it from afar, it would have appeared like a glowing cosmic whirlpool. At the center burned the newborn sun, bright and energetic. Around it, countless particles drifted in orbit, circling the star in a slow but steady dance. These particles were the leftover material from the cloud that had collapsed to form the sun. Though the star had captured most of the mass, the remaining dust and gas still contained enough material to build entire planets. At first, this disk was filled with particles so small that many were no larger than grains of sand. Yet even the tiniest pieces played a role in shaping the future of the solar system. Inside the disk, conditions were far from calm. Gas currents moved slowly through space, carrying dust along swirling paths around the young star. Some regions were slightly denser than others. Some were warmer. Others were cold and dark. These subtle differences would guide the formation of worlds. Near the sun, temperatures were extremely high. Any volatile materials, such as water ice or methane, would quickly evaporate. Only heavy, heat-resistant materials like metals and silicate rocks could remain solid. Farther from the sun, however, the environment was cooler. In those distant regions, ice could survive alongside rock and metal. This difference would later determine the types of planets that formed in different parts of the solar system. But before planets could exist, something much smaller had to happen first. Dust had to stick together. When tiny particles collide in space, they usually bounce apart. But sometimes, if the conditions are just right, they cling to one another through electrostatic forces. Gradually, over thousands of years, clusters of dust grains began forming delicate, fluffy aggregates. These fragile clumps drifted through the disk, colliding with other clumps. Some broke apart, others survived and continued growing. Bit by bit, these clumps became larger and denser. The process was slow, but it was relentless. Dust grains became pebbles. Pebbles collided with other pebbles, forming rocks. Rocks merged into objects several meters across. Eventually, some bodies grew large enough that gravity itself began helping them collect more material. Once gravity became important, growth accelerated dramatically. These growing objects became known as planetesimals. Planetesimals were the true seeds of planets. Many of them were tens of kilometers across. Some were even larger. Within the swirling disk, thousands of these rocky bodies orbited the Sun along slightly different paths. Occasionally, their orbits crossed. When two planetesimals collided, the results depended on their speed. Some impacts were gentle enough that the two bodies merged into one larger object. Others were violent, shattering the bodies into fragments that scattered through space. But over millions of years, growth generally won out over destruction. Planetesimals slowly grew larger. In some regions of the disk, these objects reached sizes of hundreds of kilometers. And once objects reached that scale, their gravity became powerful enough to influence their surroundings. They began pulling nearby rocks and dust toward themselves. Their growth entered a stage astronomers call runaway accretion. The larger a body became, the stronger its gravity grew. And the stronger its gravity became, the faster it gathered material. This feedback loop allowed certain bodies to grow rapidly into planetary embryos, large protoplanets that would eventually become the worlds we know today. Yet the story unfolding within the disk was not the same everywhere. Distance from the Sun changed everything. Close to the young star, only rocky materials could survive the intense heat. This meant that the inner regions of the solar system were limited in the types of building materials available. Planets forming here would be smaller and composed mainly of rock and metal. Farther from the Sun, where temperatures were colder, icy materials could also accumulate. Ice greatly increased the amount of solid matter available for building planets. As a result, protoplanets in the outer solar system could grow much larger. In those distant regions, enormous worlds were beginning to take shape. Among them was a giant that would eventually dominate the solar system, the future Jupiter. As Jupiter's core grew, its gravity began attracting not only solid material, but also enormous quantities of hydrogen and helium gas from the surrounding disk. Within a relatively short period of cosmic time, Jupiter became a true giant planet. Its presence dramatically reshaped the young solar system. The growing giant's gravity disturbed nearby planetesimals, sending some crashing into other worlds while ejecting others into distant orbits. Some fragments would eventually become asteroids. Others would be flung toward the outer edges of the solar system, forming distant icy reservoirs of comets. But at this early stage, the disk was still crowded with debris. Thousands upon thousands of planetesimals continued orbiting the Sun, colliding and merging as the solar system slowly assembled itself. Closer to the Sun, several planetary embryos were also taking shape. One of these embryos would eventually become Earth. Another would become Venus. Others would form Mercury and Mars. Yet at this stage, these worlds were still incomplete. They were growing through constant impacts, absorbing smaller bodies, and competing with neighboring protoplanets for material. The young solar system remained a turbulent place. The Sun itself was also more active than it is today. Young stars often produce powerful solar winds, streams of charged particles that blow outward into space. Over time, the sun's solar wind began clearing away much of the remaining gas from the protoplanetary disk. This process gradually stripped the inner solar system of its lighter gases, leaving behind primarily rocky material. The window for building giant gas planets was closing. Beyond the region where Jupiter formed, two other giants were also emerging. These worlds would eventually become Saturn, Uranus, and Neptune. Each formed in the colder outer regions where ice and gas could accumulate. Together, these massive planets would later shape the architecture of the entire solar system. But their influence had only just begun. Within the inner solar system, rocky worlds were still growing through violent collisions. Some protoplanets were destined to merge, others would be destroyed. And one of those future collisions would create something very special, a companion world that would circle Earth for billions of years, the Moon. Yet that dramatic event still lay in the future. For now, the solar system was still young. Dust had become rocks. Rocks had become planetesimals. Planetesimals were becoming worlds. And the quiet disk of gas and dust surrounding the sun was slowly transforming into a family of planets. But the most chaotic chapter of this story was still ahead, because the growing planets were about to begin colliding with one another on a truly colossal scale. The Age of Protoplanets. By the time several million years had passed since the birth of the Sun, the once smooth disk of dust and gas had changed dramatically. The tiny grains that once drifted quietly through space had grown into rocks. The rocks had merged into massive bodies known as planetesimals. And now, some of those bodies had become something even larger, protoplanets. These were the early building blocks of true planets, worlds, that were hundreds or even thousands of kilometers across. They were large enough for gravity to pull them into roughly spherical shapes, and their growing mass allowed them to dominate their local regions of the solar disk. The solar system was no longer a calm disk of dust. It had become a chaotic environment filled with competing worlds. Thousands of protoplanets orbited the Sun along slightly different paths. Some traveled closer to the star, where temperatures remained scorching hot. Others moved along colder, more distant orbits. Each of these bodies tugged gravitationally on the others. Their orbits shifted, their paths crossed. And when those paths crossed, collisions became inevitable. These collisions were not gentle. They were colossal. Two worlds hundreds of kilometers across could smash together at speeds of several kilometers per second. The energy released in such impacts was enormous enough to melt rock, vaporize metal, and send fragments flying across millions of kilometers of space. Yet despite the violence, these impacts played a crucial role in shaping the future planets. When two protoplanets collided at moderate speeds, they often merged together. The debris from the collision eventually fell back onto the larger body, adding to its mass. Through countless impacts like these, several dominant worlds began emerging in the inner solar system. One of them would eventually become Earth. Another would grow into Venus. Farther inward, a smaller world would form that we now call Mercury. And farther out, another rocky planet would emerge, Mars. But at this early stage, these worlds were still incomplete. Their surfaces were molten, their interiors were still differentiating, with heavier elements like iron sinking toward their centers, while lighter materials floated upward. As this internal rearrangement occurred, the young planets developed layered structures. Dense metallic cores formed deep inside them. Above those cores lay thick mantles of hot rock, and eventually, solid crusts began forming at their surfaces. But the bombardment of space debris constantly shattered these early crusts. The inner solar system remained an extremely dangerous place. Large planetesimals still wandered through space. Some were remnants of collisions. Others were bodies that had never successfully joined a larger planet. These wandering objects frequently crashed into the growing worlds. Each impact reshaped the surface. Each collision released enormous heat. Some impacts were so powerful that they melted entire regions of a planet's crust. Yet among all these violent encounters, one particular collision would prove especially important for the future of Earth. At the time, the young Earth was still forming. It had already grown into a large protoplanet, but its final shape had not yet been decided. Not far away, another protoplanet orbited the Sun. This body was roughly the size of Mars. Astronomers believe this world is what scientists now call Theia. For millions of years, Theia followed its orbit around the Sun, occasionally drifting closer to Earth's path. Then, sometime around 4.5 billion years ago, their paths finally crossed. The collision between Earth and Theia was catastrophic. The two worlds slammed together with unimaginable force. The impact did not simply crack the surface, it blasted enormous quantities of molten rock into space. For a brief moment, Earth may have been partially vaporized. A glowing cloud of debris surrounded the damaged planet, forming a vast ring of hot rock fragments orbiting the young Earth. But gravity soon began pulling that debris back together. Over time, the fragments collided and merged with one another. Slowly, they formed a new world. That world became the Moon. The Moon likely formed surprisingly quickly, perhaps within just a few thousand years after the collision. At first, it orbited much closer to Earth than it does today. The young Moon glowed red-hot, its surface covered by a global ocean of molten rock. Meanwhile, Earth itself remained a violent and fiery world. Its surface was dominated by oceans of magma. Volcanoes erupted constantly. Asteroids and comets continued raining down upon the planet. Yet the presence of the Moon would eventually become one of the most important factors in Earth's future. The Moon's gravity stabilizes Earth's axial tilt, helping maintain relatively stable seasons over long periods of time. It also produces the tides in Earth's oceans, movements of water that would later play a role in shaping coastal environments and perhaps even early life. But at this stage of the story, Earth and the Moon were still extremely young. Their surfaces were hostile. No oceans existed yet. No atmosphere suitable for life had formed. Still, the architecture of the inner solar system was beginning to settle. Many of the largest protoplanets had already merged into the dominant worlds that would become the 4 rocky planets. The number of large collisions gradually began decreasing. But the story was far from finished. Farther out in the solar system, enormous worlds were continuing to grow. Massive planets like Jupiter and Saturn had already become giants. Their gravity was powerful enough to influence the orbits of countless smaller bodies across the solar system. Some objects were pulled inward toward the Sun. Others were flung outward into distant regions of space. These giant planets were beginning to reshape the entire solar system. Their movements would eventually scatter debris, form asteroid belts, and send icy bodies toward the outer edges of the Sun's gravitational domain. But that part of the story was only beginning to unfold. For now, the age of protoplanets was slowly drawing to a close. The chaotic swarm of growing worlds was gradually transforming into a more stable system. A family of planets was emerging. Mercury, Venus, Earth, and Mars had taken shape in the inner solar system. Beyond them, giant planets dominated the colder outer regions, and the young Sun shone brightly at the center of it all, illuminating a planetary system that was finally beginning to resemble the one we know today. Yet even as the dust slowly settled, the solar system still had one more turbulent chapter ahead, because the giant planets were about to move. And when they did, their gravitational influence would unleash one of the most dramatic periods of bombardment in the history of the inner solar system. That event would reshape the surfaces of the young planets, including Earth, and leave scars that are still visible today. By the time tens of millions of years had passed since the birth of the Sun, the solar system had already changed dramatically from its earliest form. The swirling disk of dust that once surrounded the young star had largely disappeared. Most of its material had already been absorbed into growing planets, scattered into distant regions, or blown away by the powerful solar wind of the Sun itself. Yet the solar system was still far from peaceful. Though the major planets had formed, countless smaller bodies still remained. Fragments of planetesimals drifted through space, and many unstable orbits still crisscrossed the planetary paths. But the greatest source of change now came from the giant planets themselves. Far beyond the rocky worlds of the inner solar system, enormous planets had grown within the colder regions of the protoplanetary disk. These massive worlds, Jupiter, Saturn, Uranus, and Neptune, contained most of the remaining planetary mass after the Sun itself. Because of their immense gravity, these giants began exerting powerful influences on the rest of the solar system. Their orbits were not perfectly stable in the beginning. Instead, they slowly shifted over time in a process astronomers call planetary migration. In the early solar system, the giant planets were surrounded by large populations of icy planetesimals. Each time one of these small bodies passed near a giant planet, gravity slightly altered its orbit. Some objects were pulled inward toward the Sun, others were flung outward into deep space. But each interaction also slightly changed the orbit of the planet itself. Over millions of years, these tiny gravitational exchanges added up. The planets gradually migrated. The most massive of them all, Jupiter, moved slightly inward toward the Sun. Meanwhile, Saturn drifted outward. The outer giants, Uranus and Neptune, also shifted positions, slowly spreading farther from the Sun. These changes might sound small, but the consequences were enormous. As the giant planets moved, their gravity destabilized vast regions of the solar system. Huge numbers of leftover planetesimals were suddenly thrown into chaotic new orbits. Some were sent plunging toward the inner solar system, where they crossed the paths of the rocky planets. This triggered a period known to scientists as the Late Heavy Bombardment. During this time, enormous numbers of asteroids and comets rained down on the inner planets. The impacts were relentless. Crater after crater formed across the surfaces of Mercury, Venus, Earth, and Mars. On Earth, many of these early craters have long since been erased by geological activity. But on airless worlds like the Moon, the scars of that violent era are still clearly visible. The Moon's heavily cratered surface is a frozen record of this ancient storm of impacts. Some of the collisions during the Late Heavy Bombardment were truly enormous. Asteroids hundreds of kilometers wide slammed into planetary surfaces at speeds exceeding tens of kilometers per second. The energy released during such impacts could melt entire regions of crust and reshape planetary landscapes. Yet, despite the violence, these impacts also delivered something valuable. Many of the incoming bodies were rich in water and organic molecules. When icy comets and water-bearing asteroids struck the young Earth, they may have contributed to the formation of the planet's early oceans. These impacts also delivered carbon-containing compounds that would later become important ingredients for life. In this way, The chaos of the early solar system may have helped prepare the conditions that eventually allowed life to arise on Earth. Meanwhile, not all of the scattered planetesimals collided with planets. Some were trapped in stable regions of space. Between the orbits of Mars and Jupiter, many rocky fragments gathered into a region now known as the asteroid belt. These objects are the leftover building blocks of a planet that never formed. Jupiter's powerful gravity constantly disturbed their orbits, preventing them from merging into a single world. Instead, the asteroid belt became a vast collection of rocky bodies ranging in size from tiny dust grains to dwarf planets hundreds of kilometers wide. Farther out in the solar system, another enormous reservoir of icy bodies formed. Beyond the orbit of Neptune lies a region called the Kuiper Belt. This distant zone contains countless frozen remnants of the early solar system. Among them are dwarf planets such as Pluto, along with many other icy worlds that continue orbiting quietly in the darkness far from the Sun. Even beyond the Kuiper Belt lies an even more distant and mysterious region. Astronomers believe that trillions of icy objects form a vast spherical cloud surrounding the solar system. This region is known as the Oort cloud. It may extend halfway to the nearest stars. Occasionally, gravitational disturbances send one of these icy bodies falling inward toward the Sun. When that happens, we see them as long-period comets blazing across the night sky. By scattering debris into these distant reservoirs, the giant planets helped clear most of the remaining clutter from the solar system. Gradually, the chaotic swarm of planetesimals diminished. The frequency of impacts decreased. The planetary orbits became more stable, and the solar system began settling into the orderly structure we recognize today. At the center shone the Sun. Closest to it orbited the four rocky worlds: Mercury, Venus, Earth, and Mars. Farther out moved the giant planets, Jupiter and Saturn, followed by the icy giants Uranus and Neptune. Beyond them stretched belts of asteroids and comets, remnants of the solar system's violent youth. What had once been a chaotic disk of dust and gas had finally matured into a planetary system. But the story of the solar system was far from over. Because while the planets now followed relatively stable paths around the Sun, the surfaces of those worlds were still evolving. Volcanoes would shape landscapes. Atmospheres would form and change. Oceans might appear. And on one small rocky world, orbiting at just the right distance from the Sun, something extraordinary would eventually happen. Chemistry would become biology. Life would begin. Building the planets, the inner worlds begin to take shape. Long after the great cloud of gas and dust collapsed to form the young Sun, the solar system had begun settling into a recognizable structure. The violent age of planet formation was slowly calming. The enormous collisions that once dominated the early solar system had become less frequent, and the number of wandering planetesimals had greatly decreased. Yet the young planets were still far from the stable worlds we know today. They were hot, restless, and constantly changing. The four rocky planets closest to the Sun, Mercury, Venus, Earth, and Mars, were born in a region of the solar system where temperatures were extremely high. In this inner region, only materials with high melting points could survive the heat of the young Sun. Metals such as iron and nickel, along with rocky minerals made from silicon and oxygen, became the primary building blocks of the inner planets. Lighter elements, like hydrogen and helium, so abundant in the outer solar system, were mostly blown away from this region by the intense solar wind of the young Sun. As a result, the inner planets became dense, rocky worlds. At first, their surfaces were not solid ground as we imagine today. Instead, they were covered by vast oceans of molten rock. The enormous heat produced during planet formation came from several sources. First, the countless collisions that built the planets released tremendous amounts of energy. Every time a large object struck a young planet, the impact generated heat powerful enough to melt huge regions of crust. Second, as the planets grew larger, gravity compressed their interiors. This compression generated additional heat deep within the planets. And third, radioactive elements trapped inside the young planets slowly decayed, producing heat that helped keep their interiors molten. The result was a collection of glowing, fiery worlds. But over time, something remarkable began happening inside these molten planets. The materials within them started separating. This process is known as planetary differentiation. Heavier elements, such as iron and nickel, slowly sank toward the centers of the planets under the pull of gravity. Meanwhile, lighter materials rose toward the surface. Gradually, each planet developed an internal structure. At the center formed a dense metallic core. Above the core lay a thick mantle made mostly of hot rock, and eventually, a thin outer crust began forming as the surfaces slowly cooled. This layering would later play a critical role in shaping the geological activity of each planet. Yet, despite these similarities, the inner planets did not all evolve in the same way. Each one followed a different path. Each became a unique world. The closest of them to the Sun was Mercury. Mercury formed in the most extreme environment of the inner solar system. It orbits the Sun at an average distance of only about 58 million kilometers, meaning it receives intense solar radiation. Because of this proximity, temperatures on Mercury can reach scorching levels during the day. Yet, surprisingly, Mercury also experiences some of the coldest temperatures in the solar system at night. This dramatic temperature difference occurs because Mercury has almost no atmosphere to trap heat. Its thin exosphere, composed of a few scattered atoms, is far too weak to retain warmth. Mercury's small size also played a role in shaping its history. Because the planet contains relatively little mass, it lost much of its internal heat relatively quickly. As a result, Mercury's geological activity faded early in its history. Today, its surface is heavily cratered, resembling the battered terrain of the Moon. Gigantic impact basins mark the surface, silent reminders of the violent early solar system. One of the largest of these basins is the Caloris Basin, a colossal crater created by an ancient asteroid impact. Yet, despite its scarred surface, Mercury holds an interesting mystery. Its metallic core is enormous compared to the size of the planet, so large that it occupies most of Mercury's interior. Scientists believe this may be the result of a massive collision early in the planet's history, which may have stripped away much of its original outer layers. Such violent events were common during the early age of planet formation. While Mercury endured its harsh destiny close to the Sun, another world was forming not far beyond it. This planet would become one of the most mysterious and hostile environments in the solar system. That world was Venus. In size, Venus is remarkably similar to Earth. In fact, it is often called Earth's twin because their diameters differ by only a few hundred kilometers. Yet the two planets would evolve in dramatically different ways. Early in its history, Venus may have looked very similar to Earth. Some scientists believe it may even have had oceans of liquid water. But over time, powerful greenhouse effects transformed Venus into a world of extreme heat. Thick layers of carbon dioxide built up in its atmosphere, trapping enormous amounts of solar energy. Today, the surface temperature on Venus is hot enough to melt lead. Its dense atmosphere is more than 90 times thicker than Earth's. Clouds of sulfuric acid swirl through its skies, reflecting sunlight and hiding the planet's surface beneath an eternal blanket of clouds. No spacecraft has survived long on the surface of Venus. The pressure there is so intense that it would feel like standing nearly a kilometer beneath the surface of Earth's oceans. Yet despite these harsh conditions, Venus remains one of the most fascinating worlds in the solar system, because it reminds us how small differences during planetary formation can lead to drastically different outcomes. Meanwhile, between the orbits of Venus and Mars, another planet was continuing its long journey toward becoming a very special world. A planet that would one day host oceans, continents, and life itself. That planet was Earth. But Earth's story, and how it became a habitable world, deserves a chapter of its own. When the young Earth first formed, it looked nothing like the peaceful blue planet we know today. There were no oceans, no continents, no clouds drifting across a blue sky. Instead, the early Earth was a violent and glowing world, its surface covered by vast oceans of molten rock. This fiery beginning was the result of the enormous energy released during planet formation. As countless planetesimals collided and merged to form the growing planet, each impact released tremendous heat. The young Earth absorbed that energy, keeping much of its surface melted for millions of years. Deep inside the planet, gravity was performing another quiet but powerful transformation. Heavier elements, such as iron and nickel, slowly sank toward the center of the planet, pulled inward by gravity. Lighter materials floated upward toward the surface. This process, called planetary differentiation, created the layered structure that still exists inside Earth today. At the center formed a dense metallic core. Above that core lay the mantle, a thick layer of hot rock that slowly circulates over time. And above the mantle, a thin crust eventually began to form as the surface cooled. Yet the cooling of Earth's surface was not a smooth or peaceful process. For millions of years, enormous volcanoes erupted constantly. Vast rivers of lava flowed across the planet's surface, reshaping the landscape again and again. At the same time, the young Earth continued to endure frequent impacts from asteroids and comets, remnants of the early solar system that still wandered through unstable orbits. Each impact released new bursts of heat, sometimes melting entire regions of crust and sending clouds of vaporized rock high into the sky. But slowly, as millions of years passed, the number of impacts began to decrease, and the surface of Earth gradually cooled. As it cooled, something remarkable began to happen. The planet started to form an atmosphere. Unlike the thick atmosphere we breathe today, Earth's first atmosphere was very different. It did not come from captured gas drifting through space. Instead, it formed from gases released by volcanic eruptions deep within the planet. Volcanoes spewed enormous amounts of gas into the air: carbon dioxide, nitrogen, water vapor, and smaller amounts of other compounds. Over time, these gases built up into a dense and cloudy atmosphere surrounding the young Earth. The sky above the planet would have looked dark and hazy, filled with thick clouds of volcanic gases. Among those gases was one particularly important ingredient: water vapor. At first, the temperatures on Earth remained too high for water to exist as liquid. The water released by volcanoes stayed suspended in the atmosphere as steam. But as the planet continued cooling, the atmosphere eventually reached a critical point. The steam began to condense, clouds thickened across the sky, and then, for the first time in Earth's history, rain began to fall. Not gentle rain like we experience today. This was a planetary storm unlike anything seen before. Rain poured from the skies for thousands, perhaps even millions of years. The water collected in low regions of the cooling crust, gradually forming the first primitive oceans. Some of this water may also have arrived from space. Many of the asteroids and comets striking the young Earth contained ice locked within their rocky interiors. When these bodies collided with Earth, they released water that contributed to the growing oceans. Over time, these two sources, volcanic outgassing and icy impacts, combined to fill vast basins with water. Eventually, enormous oceans covered much of the planet's surface. For the first time, Earth began to resemble a water world. But the presence of oceans did more than simply transform the planet's appearance. Water became a powerful force shaping Earth's future. The oceans helped regulate temperature by absorbing heat from the sun. They also dissolved carbon dioxide from the atmosphere, slowly reducing the greenhouse effect that had once dominated the planet. Meanwhile, deep within the planet, the interior remained hot and active. The movement of heat from Earth's interior caused the crust to crack and shift. Large sections of the crust began slowly moving across the surface, a process we now call plate tectonics. These moving plates created mountains, volcanoes, and ocean trenches. They constantly reshaped Earth's surface over millions of years. Plate tectonics would later play a crucial role in maintaining Earth's habitability by recycling carbon between the atmosphere, oceans, and rocks. But even as these geological processes began shaping the young Earth, another important influence continued quietly working from space. High above the planet, the Moon orbited the Earth. The Moon had formed earlier from the enormous collision between Earth and the protoplanet Theia. After its formation, it orbited much closer to Earth than it does today. At that time, the Moon would have appeared enormous in the sky, several times larger than it looks today. Its gravitational pull created powerful tides in the young oceans. These tides constantly moved water back and forth across shallow coastal regions, mixing chemicals and minerals in complex ways. Some scientists believe these tidal movements may have played an important role in the chemistry that eventually led to life. But at this stage of the story, life had not yet appeared. The oceans were still hot. The atmosphere lacked oxygen. The planet was still experiencing occasional asteroid impacts. Yet despite these harsh conditions, Earth was slowly becoming more stable. Its crust thickened, its oceans deepened, its atmosphere evolved. The planet was quietly preparing itself for something extraordinary. Meanwhile, farther out in the solar system, another rocky world was following its own path of transformation. Unlike Earth, this world would gradually lose most of its atmosphere and water. Over billions of years, it would become a cold desert world covered with dust and ancient volcanoes. That world was Mars. Beyond the orbit of Earth, another rocky world formed during the chaotic early days of the solar system. Today we know this planet as Mars, the red planet. Seen from Earth, Mars glows faintly in the night sky with a reddish color that has fascinated human observers for thousands of years. Ancient civilizations often associated this mysterious red light with war and fire. Yet the true story of Mars is far more complex and far more intriguing than early skywatchers could ever have imagined. Like the other rocky planets, Mars began its existence as a growing protoplanet inside the dusty disk surrounding the young Sun. Countless small planetesimals collided and merged, gradually building a world made mostly of rock and metal. For a time, the young Mars may have looked somewhat similar to the early Earth. Its interior was hot, volcanoes erupted across its surface, and its atmosphere was likely thicker than it is today. Scientists now believe that early Mars once possessed flowing rivers, lakes, and perhaps even shallow oceans. Evidence of this watery past is still visible across the planet's ancient terrain. Orbiting spacecraft and robotic explorers have discovered enormous dried river valleys carved into the Martian surface. These valleys twist and branch in patterns remarkably similar to river systems on Earth. Some of these channels stretch for hundreds of kilometers. Others appear to have once fed into large basins that may have been ancient lakes. In fact, one region of Mars, known as Jezero Crater, now explored by the Perseverance rover, contains clear evidence of an ancient river delta. Long ago, water likely flowed into this crater, depositing layers of sediment that scientists now study in search of possible signs of ancient life. But Mars was never destined to follow the same path as Earth. The key difference between the two planets lies in their size. Mars is only about half the diameter of Earth, and its mass is much smaller. Because of this, the planet's gravity is weaker. That difference had enormous consequences for Mars's long-term evolution. Inside Earth, the large size of the planet allowed its interior to remain hot and active for billions of years. This internal heat drives plate tectonics and maintains a powerful magnetic field generated within Earth's core. Mars, however, cooled much more quickly. As the planet lost its internal heat, its geological activity gradually slowed. The planet's core began to solidify, and its magnetic field weakened. Eventually, the global magnetic field that once protected Mars disappeared almost entirely. Without that magnetic shield, the planet became vulnerable to the powerful solar wind streaming outward from the sun. Over millions of years, this constant stream of charged particles began stripping away Mars's atmosphere. The thicker atmosphere that may once have supported rivers and lakes slowly vanished into space. As the atmosphere thinned, the surface pressure on Mars dropped dramatically. Liquid water could no longer remain stable on the surface. The rivers dried. The lakes disappeared. Whatever oceans may have existed gradually evaporated or froze beneath the soil. Mars slowly transformed into the cold, desert world we see today. Yet, even as the planet cooled and dried, Mars continued to produce some of the most impressive geological features in the entire solar system. One of the most remarkable of these features is Olympus Mons. Olympus Mons is the largest volcano known in the solar system. It towers nearly 22 kilometers above the surrounding plains, almost 3 times the height of Mount Everest on Earth. Its base stretches across an area roughly the size of the state of Arizona. This enormous volcano formed because Mars lacks the moving tectonic plates that constantly reshape Earth's surface. On Earth, volcanic hotspots shift as plates move across them, forming chains of volcanoes over time. But on Mars, the crust remained largely stationary. As a result, lava continued erupting from the same location for millions of years, gradually building a single, gigantic volcano. Mars also contains another astonishing geological feature. Stretching across much of the planet's surface is an immense canyon system known as Valles Marineris. This canyon network extends more than 4,000 kilometers across Mars, nearly the width of the United States. In some places, its cliffs plunge more than 7 kilometers deep. If placed on Earth, Valles Marineris would dwarf even the Grand Canyon. The formation of this enormous canyon system is likely related to the stretching and cracking of the Martian crust as the planet cooled and contracted over time. Today, Mars is a world of extremes. Its thin atmosphere offers little protection from solar radiation. Temperatures can plunge far below freezing during the long Martian nights. Dust storms sometimes grow so large that they cover the entire planet. Yet, despite these harsh conditions, Mars remains one of the most fascinating places in the solar system. Scientists continue exploring the planet with robotic spacecraft and rovers, searching for clues about its ancient past. One of the most important questions researchers hope to answer is whether life ever existed on Mars. If the planet once had stable bodies of water, thicker atmospheres, and warmer climates, it may have provided suitable environments for simple microbial life billions of years ago. So far, no definitive evidence of past life has been found, but the search continues. Mars holds many secrets, buried beneath its dusty surface, and each new mission brings us a little closer to understanding the history of this mysterious world. Yet Mars is only one chapter in the larger story of planetary evolution. Beyond the rocky worlds of the inner solar system lie planets of an entirely different kind. Colossal giants made mostly of gas and ice. These enormous worlds contain the majority of planetary mass in the solar system. Their gravity shapes the orbits of countless smaller objects, and their moons form miniature planetary systems of their own. To understand the full story of the solar system, we must now travel outward, beyond the orbit of Mars. There, we will encounter the largest planet of them all, a swirling giant of storms and clouds known as Jupiter. Far beyond the rocky worlds of Mercury, Venus, Earth, and Mars, the solar system changes dramatically. Here, in the colder and darker regions far from the warmth of the sun, entirely different kinds of planets were born. These are the giant planets, enormous worlds made mostly of gas and ice rather than solid rock. They are vastly larger than the inner planets, and together they contain most of the planetary mass in the solar system. Their immense gravity shapes the structure of the entire solar system, influencing the orbits of asteroids, comets, and even the smaller planets closer to the Sun. The first of these giants is the largest planet in the solar system, Jupiter. Jupiter formed in a region of the early solar system where temperatures were low enough for ice to exist. This made a tremendous difference during planet formation. In the colder outer regions, ice joined rock and metal as building materials for growing planets. This allowed protoplanets to accumulate mass much more quickly than those in the hotter inner solar system. As a result, Jupiter's core grew rapidly. Once this core reached a critical size, about 10 times the mass of Earth, its gravity became strong enough to capture enormous quantities of gas from the surrounding protoplanetary disk. Hydrogen and helium poured inward, forming a vast atmosphere around the growing planet. Within a relatively short time, Jupiter had become a true giant. Today, Jupiter is more than twice as massive as all the other planets combined. Yet, despite its enormous size, Jupiter is not a solid world. Its outer layers consist of thick clouds swirling through a deep atmosphere made mostly of hydrogen and helium. Beneath these clouds, pressure increases rapidly. The gas becomes compressed into strange forms that do not exist naturally on Earth. Deep inside the planet, hydrogen may even behave like a liquid metal, conducting electricity and helping generate Jupiter's powerful magnetic field. One of the most famous features on Jupiter is the Great Red Spot. This enormous storm has been raging for at least 3 centuries, and possibly much longer. The Great Red Spot is so large that it could easily swallow the entire Earth. Powerful winds swirl around the storm at hundreds of kilometers per hour, creating a gigantic vortex that has persisted for generations of human observers. But Jupiter's influence extends far beyond its own atmosphere. Because of its enormous gravity, Jupiter plays a crucial role in shaping the solar system. many asteroids that might otherwise threaten the inner planets are deflected or captured by Jupiter's gravity. In this way, Jupiter sometimes acts like a cosmic shield, reducing the number of dangerous objects reaching worlds such as Earth. Yet Jupiter is not alone among the giants. Orbiting farther from the Sun is another magnificent world, Saturn. Saturn is slightly smaller than Jupiter, but still enormous compared to the rocky planets. Like Jupiter, Saturn is composed mostly of hydrogen and helium. Its atmosphere is filled with colorful bands of clouds and powerful winds that circle the planet at incredible speeds. But Saturn is most famous for something truly spectacular: its rings. The rings of Saturn are among the most beautiful structures in the solar system. They appear as bright bands encircling the planet, visible even through small telescopes from Earth. Yet these rings are not solid structures. Instead, they consist of countless particles of ice and rock, ranging in size from tiny grains to chunks as large as houses. Each of these particles orbits Saturn independently, following the laws of gravity, just like miniature moons. Scientists believe the rings may have formed when a moon or icy body wandered too close to Saturn and was torn apart by tidal forces. The debris from that shattered object spread into orbit around the planet, gradually forming the ring system we see today. Although Saturn's rings appear massive, they are surprisingly thin. In many places, they are only tens of meters thick. Despite their delicate structure, the rings form an intricate and constantly shifting pattern, shaped by the gravitational influence of Saturn's many moons. And Saturn has many moons indeed. More than 80 have been discovered so far, including one particularly fascinating world, Titan. Titan is larger than the planet Mercury and possesses a thick atmosphere rich in nitrogen. Its surface hosts rivers, lakes, and seas, not of water, but of liquid methane and ethane. Titan is one of the most intriguing places in the solar system for scientists studying planetary atmospheres and the chemistry that might resemble conditions on the early Earth. Beyond Saturn lie two more giant planets, though they differ somewhat from Jupiter and Saturn. These worlds are often called the ice giants. The first of them is Uranus. Uranus is unique among the planets because of its unusual orientation. Instead of spinning upright like most planets, Uranus rotates on its side, with its axis tilted by about 98 degrees. This means that during parts of its long orbit around the Sun, one pole of Uranus points almost directly toward the Sun, while the other lies in darkness. As a result, the planet experiences extremely unusual seasons that last for decades. Scientists suspect that this strange tilt may have been caused by a massive collision early in the planet's history. Like the other giant planets, Uranus is surrounded by a system of rings and moons. Its pale blue color comes from methane gas in its atmosphere, which absorbs red light and reflects blue wavelengths back into space. Even farther out lies the final giant planet, Neptune. Neptune is the most distant major planet in the solar system. Despite its great distance from the Sun, Neptune is a remarkably dynamic world. Its atmosphere contains some of the fastest winds in the solar system, reaching speeds of more than 2,000 kilometers per hour. Like Jupiter, Neptune has enormous storms that appear as dark spots in its atmosphere. These storms form and disappear over time, driven by powerful atmospheric currents deep within the planet. Neptune's largest moon, Triton, is also an extraordinary place. Triton orbits Neptune in the opposite direction of the planet's rotation, a clue that it may have formed elsewhere and was later captured by Neptune's gravity. The moon's surface is covered with frozen nitrogen and strange cryovolcanoes that erupt icy material instead of molten rock. Together, these giant planets form a vast outer realm of the solar system. Their gravity continues to influence countless smaller objects, asteroids, comets, and icy remnants left over from the formation of the planets. Beyond their orbits lies a distant region filled with frozen bodies and ancient debris from the earliest days of the solar system. It is a place where dwarf planets drift slowly through darkness. A region known as the Kuiper Belt. And still farther beyond that lies an even more mysterious frontier. A vast cloud of icy objects that may extend halfway to the nearest stars. Far beyond the orbits of the giant planets, beyond Jupiter, Saturn, Uranus, and Neptune, the solar system slowly fades into a cold and mysterious frontier. Here, sunlight grows weak. The warmth of the sun becomes only a faint glow in the sky, barely brighter than the surrounding stars. Temperatures fall to hundreds of degrees below freezing, and the landscape of this distant region is dominated not by rocky planets or massive gas giants, but by countless frozen remnants left over from the birth of the solar system. This distant region is known as the Kuiper Belt. The Kuiper Belt is a vast ring of icy bodies orbiting the Sun beyond Neptune. It stretches across billions of kilometers of space and contains millions, perhaps even billions of objects made primarily of ice, rock, and frozen gases. These objects are sometimes called trans-Neptunian objects, meaning they orbit farther from the Sun than Neptune. Many of them are small, only a few kilometers across. But some are surprisingly large. Among the most famous of these distant worlds is Pluto. For many decades, Pluto was considered the 9th planet of the solar system. Discovered in 1930, it quickly captured the imagination of astronomers and the public alike. But as telescopes improved, scientists began discovering more and more objects in the same distant region of space. Some of these objects were nearly as large as Pluto. Eventually, astronomers realized that Pluto was not alone. It was simply the largest known member of a vast population of icy worlds. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet. Though this change surprised many people, it helped scientists better understand the true structure of the solar system. Pluto remains one of the most fascinating worlds ever discovered. Despite its small size, only about 2/3 the diameter of Earth's moon, Pluto possesses a surprisingly complex landscape. Its surface is covered with frozen plains, towering mountains made of water ice, and vast regions of frozen nitrogen and methane. One of the most famous features on Pluto is a bright, heart-shaped region known as Tombaugh Regio. This enormous plain of frozen nitrogen stretches across a large portion of the dwarf planet's surface. Within this region lies a vast basin called Sputnik Planitia, where slow-moving glaciers of nitrogen ice creep across the landscape over millions of years. The remarkable details of Pluto's surface were revealed in 2015 when the spacecraft New Horizons made its historic flyby of the distant world. After traveling for nearly a decade through deep space, New Horizons passed within about 12,500 kilometers of Pluto, capturing the first close-up images of this mysterious frontier planet. The photographs stunned scientists. Instead of a frozen, lifeless ball, Pluto turned out to be a geologically active world with mountains, glaciers, and complex surface patterns. It was a reminder that even the smallest worlds in the solar system can hold extraordinary surprises. But Pluto is not the only dwarf planet in the Kuiper Belt. Another intriguing object in this region is Eris. Eris is slightly smaller than Pluto, but more massive, and its discovery played a major role in the debate that led to Pluto's reclassification. Other known dwarf planets in this distant region include Haumea and Makemake. Each of these worlds follows its own slow orbit around the Sun, taking hundreds of years to complete a single journey. Haumea is particularly unusual. Unlike most round planets, Haumea has an elongated shape that resembles a flattened football. This shape is likely the result of a massive collision in the distant past that spun the dwarf planet into its current form. Haumea also possesses its own ring system and several small moons. The Kuiper belt itself is far larger than the asteroid belt located between Mars and Jupiter. While the asteroid belt contains mostly rocky debris, the Kuiper belt is rich in frozen materials. These icy bodies are remnants of the early solar system objects that never merged into larger planets. They are, in a sense, time capsules from the era when the solar system first formed billions of years ago. Occasionally, gravitational interactions disturb the orbits of these distant objects. When that happens, one of these icy bodies may begin a long journey toward the inner solar system. As it approaches the Sun, the increasing heat causes its surface ice to vaporize. Gas and dust stream away from the object, forming a glowing tail that can stretch millions of kilometers through space. At that moment, the object becomes something truly beautiful: a comet. Comets have fascinated human observers for centuries. In ancient times, they were often viewed as omens or mysterious signs in the sky. But today, we know they are visitors from the outer reaches of the solar system. Each comet carries with it frozen materials that formed billions of years ago, during the earliest stages of planetary formation. In this way, comets serve as messengers from the distant past. They carry clues about the conditions that existed when the solar system was still young. Yet the Kuiper belt is not the outermost boundary of the Sun's influence. Far beyond this region lies an even more distant and mysterious realm, a vast cloud of icy bodies that may extend tens of thousands of astronomical units into space. This region is known as the Oort cloud. Unlike the flat disk of the Kuiper belt, the Oort cloud is believed to form a spherical shell surrounding the entire solar system. Trillions of icy objects may drift slowly within this distant cloud. From time to time, the gravitational pull of passing stars disturbs one of these distant bodies, sending it falling inward toward the Sun. When that happens, a long-period comet begins its slow journey across the solar system. Some of these comets may take millions of years to complete a single orbit. They travel from the coldest outer edges of the Sun's gravitational reach to the warm inner regions near the planets. Eventually, most of them are either ejected back into deep space or broken apart by the heat of the Sun. But their brief appearance in the night sky offers a glimpse of the distant frontier where our solar system fades into the vast darkness between the stars. If we continue traveling outward beyond the distant worlds of the Kuiper belt, the solar system becomes quieter, darker, and increasingly mysterious. The scattered dwarf planets and icy fragments that orbit in the Kuiper belt slowly become fewer. The Sun itself appears dimmer, shrinking into a small but brilliant star shining in a vast field of darkness. Yet even here, thousands of billions of kilometers from the Sun, the influence of our star has not yet ended. Far beyond the Kuiper belt lies one of the most enormous and mysterious structures in the solar system, a vast spherical cloud of icy objects known as the Oort cloud. The Oort cloud is difficult to imagine because of its sheer size. While planets orbit the Sun within a relatively flat disk, the Oort cloud surrounds the solar system in all directions. It forms a giant spherical halo that may extend tens of thousands of astronomical units into space. To understand this scale, it helps to remember that one astronomical unit, the distance between Earth and the Sun, is about 150 million kilometers. Neptune, the outermost major planet, orbits at about 30 astronomical units from the Sun. But the Oort cloud may extend as far as 50,000 or even 100,000 astronomical units away. At those distances, the Sun appears only slightly brighter than other stars in the night sky. Yet its gravitational influence still holds these distant icy bodies loosely in orbit. Scientists believe the Oort cloud formed very early in the history of the solar system, when the giant planets such as Jupiter, Saturn, Uranus, and Neptune were still migrating through the protoplanetary disk. Their immense gravity scattered countless icy planetesimals outward. Many of these objects were thrown completely out of the solar system, escaping forever into interstellar space. But some were only partially ejected. Their orbits were stretched into extremely large ellipses that carried them far away from the Sun. Over time, gravitational influences from passing stars and the tidal forces of the Milky Way galaxy gradually reshaped these elongated orbits. Instead of remaining within the flat plane of the planets, the objects became scattered in all directions. The result was the formation of the enormous spherical cloud we now call the Oort cloud. Although we cannot directly see the Oort cloud with telescopes, astronomers know it must exist. The evidence comes from the comets that occasionally appear in the inner solar system. Some comets have short orbital periods and originate in the Kuiper belt, but others follow extremely long and distant paths around the Sun. These are known as long-period comets. A long-period comet may take tens of thousands or even millions of years to complete a single orbit around the Sun. Such enormous orbits suggest that these comets originate far beyond the Kuiper belt. Their true home is believed to be the distant Oort cloud. Every so often, something disturbs one of these distant icy bodies. A nearby passing star may tug gently on the cloud, or the slow gravitational tides of the Milky Way galaxy may slightly alter an object's orbit. Even small disturbances can have dramatic consequences when objects are so far from the Sun. A slight change in motion may send a comet falling inward toward the center of the solar system. For thousands of years, the comet slowly travels through the darkness of space. At first, nothing about it appears unusual. It is simply a small frozen object drifting silently through the distant reaches of a Sun's domain. But as the comet moves closer to the Sun, the environment begins to change. Sunlight grows stronger. Temperatures slowly rise. The frozen ices that make up the comet's surface begin to warm. Eventually, the heat becomes strong enough to cause those ices to sublimate, changing directly from solid ice into gas. As the gas escapes from the comet's surface, it drags dust particles along with it. These gases and dust form a glowing cloud around the comet, known as a coma. Solar radiation and the solar wind then push some of this material away from the comet, forming a long, luminous tail that can stretch millions of kilometers through space. When viewed from Earth, this glowing tail can create one of the most beautiful sights in the night sky. Throughout human history, such comets have inspired wonder, fear, and curiosity. But today, we understand that each comet is a traveler from the most distant regions of the solar system, a messenger carrying ancient material that formed when the solar system was still young. These icy visitors provide scientists with valuable clues about the early chemistry of the solar nebula that gave birth to the planets. Yet the Oort cloud marks more than just the birthplace of long-period comets. It also represents the outermost boundary of the Sun's gravitational kingdom. Beyond this distant cloud, the Sun's influence becomes increasingly weak. At some point, the gravity of nearby stars begins to dominate. The solar system gradually blends into the vast environment of interstellar space. This boundary is not a sharp line, but a gradual transition between the Sun's domain and the broader galaxy. Still, there is a region where scientists often consider the solar system to effectively end. This is the region where the outward flow of charged particles from the Sun, known as the solar wind, finally slows and mixes with the thin gas that fills interstellar space. That distant boundary is called the heliopause, and crossing that boundary is an extraordinary milestone. Only a handful of human-made spacecraft have ever reached that distant frontier. Their journeys mark humanity's first steps beyond the protective bubble created by our Sun. As we travel farther outward from the distant icy bodies of the Oort cloud, the solar system gradually begins to fade into the immense darkness between the stars. At these extreme distances, the Sun no longer dominates the sky. Instead, it appears as just another bright star among countless others scattered across the vastness of the Milky Way galaxy. And yet, even here, far beyond the planets, beyond the comets, beyond the frozen debris left over from the formation of the solar system, the Sun still shapes the environment of space, not through gravity alone, but through an invisible stream of particles constantly flowing outward from its surface. This stream is known as the solar wind. The solar wind is composed of charged particles, mostly protons and electrons, that escape from the Sun's outer atmosphere at incredible speeds. These particles spread outward in every direction, traveling millions of kilometers into space. As they move outward, they carry with them the Sun's magnetic field. Together, the solar wind and magnetic field create an enormous protective bubble surrounding the solar system. This vast region is known as the heliosphere. The heliosphere is truly enormous. It extends far beyond the orbit of Neptune, encompassing the Kuiper Belt and even reaching out toward the distant regions near the Oort cloud. Within this giant bubble, the solar wind dominates the environment of space. Charged particles from the Sun race outward, shaping the behavior of cosmic radiation and interacting with the magnetic fields of planets throughout the solar system. In many ways, the heliosphere acts like a protective shield. It helps block a portion of the high-energy cosmic rays that constantly stream through the galaxy. Without this protective bubble, the radiation environment within the solar system might be far more intense. But even the solar wind cannot continue forever. Eventually, as it travels farther from the Sun, it begins to encounter the thin gas and magnetic fields that exist between the stars. This region is known as interstellar space. With the outward pressure of the solar wind finally balances with the pressure of the surrounding interstellar medium, a boundary forms. This boundary is called the heliopause. The heliopause marks the outer edge of the Sun's influence as carried by the solar wind. Inside this boundary lies the Sun's domain. Beyond it begins the vast ocean of interstellar space. For most of human history, the heliopause was purely theoretical. Astronomers predicted its existence, but no spacecraft had ever traveled far enough to reach it. The distances involved are truly staggering. Even the fastest spacecraft ever launched from Earth take decades to travel across the solar system. But in the late 20th century, humanity began sending explorers on journeys that would one day reach this distant frontier. Among the most famous of these explorers are two spacecraft launched in 1977, Voyager 1 and Voyager 2. Originally, the Voyager missions were designed to study the giant planets. Both spacecraft successfully flew past Jupiter and Saturn, sending back spectacular images and valuable scientific data. Voyager 2 later continued on to visit Uranus and Neptune, becoming the only spacecraft ever to explore those distant worlds up close. After completing their planetary missions, both spacecraft continued traveling outward. Decades passed. The planets slowly fell behind them. The sun grew smaller and dimmer. Yet the Voyagers continued their silent journey through space. Finally, in 2012, Voyager 1 crossed the heliopause and entered interstellar space. It became the first human-made object ever to leave the protective bubble of the heliosphere. 6 years later, in 2018, Voyager 2 followed, also passing beyond the heliopause. Even now, both spacecraft continue traveling outward. Their signals grow weaker each year as they move farther away from Earth. But they still transmit valuable data about the mysterious environment that exists between the stars. Each spacecraft also carries a special message. Attached to their sides are Golden Records metal discs containing sounds and images from Earth. These records include greetings in dozens of human languages, music from many cultures, and images representing life on our planet. They are intended as a message to any intelligent civilization that might one day discover these wandering machines. It is an extraordinary thought. Long after humanity itself may be gone, the Voyager spacecraft will continue drifting through the galaxy. They will carry with them a small record of who we were and where we came from. Yet even the Voyagers have only begun their journey. The nearest star system, Alpha Centauri, lies more than 4 light-years away. At their current speed, the Voyager spacecraft would need tens of thousands of years to travel that far. For now, they remain travelers in the vast outer darkness surrounding our solar system. Their journey reminds us of just how immense the universe truly is, and how small our solar system appears within the endless sea of stars. But the story of the solar system does not end at its outer boundary. Because while spacecraft continue exploring its distant edges, the planets themselves continue evolving. Their atmospheres shift, their surfaces change, and on one small world orbiting quietly around the sun, life has emerged, watching the stars and wondering about its place in the universe. The solar system's journey through the galaxy. Beyond the distant boundary of the heliopause, where the protective bubble of the heliosphere fades into the surrounding darkness, the solar system becomes part of something far greater: the space between the stars. Out here, the influence of the sun slowly gives way to the vast gravitational structure of the Milky Way galaxy. The solar system, which once seemed so immense when viewed from Earth, is revealed to be only a tiny neighborhood inside a much larger cosmic city. Our galaxy contains hundreds of billions of stars. Each of those stars may have its own planets, moons, asteroids, and comets. Many of those distant systems may be as rich and complex as our own solar system. And yet, despite the unimaginable scale of the galaxy, our sun follows a quiet and steady path within it. The sun is not fixed in place. Like every other star in the Milky Way, it is constantly moving. Together with its family of planets, the Sun slowly orbits around the center of the galaxy. This journey takes an extraordinary amount of time. To complete one full orbit around the galactic center requires roughly 225 to 250 million years. Astronomers sometimes call this enormous span of time a galactic year. The last time the solar system was in its current position in the galaxy, dinosaurs had not yet appeared on Earth. In fact, the continents on Earth were arranged in completely different shapes. Life itself was still evolving in ways that would eventually lead to the creatures that would one day gaze up at the night sky. And during all of that time, the Sun and its planets continued their slow voyage around the galaxy. The path of the solar system through the Milky Way is not perfectly smooth. The galaxy is filled with clouds of gas and dust, regions where new stars are born. There are also clusters of stars, swirling spiral arms, and the faint gravitational influence of dark matter shaping the entire structure of the galaxy. As the solar system travels through this cosmic environment, it occasionally passes through different regions of the galaxy. Sometimes these regions are dense with interstellar gas. Other times, they are relatively empty. Over millions of years, these changes may subtly influence the outer regions of the solar system. Passing stars may gently tug on distant icy bodies in the Oort cloud. These gravitational disturbances can send comets drifting inward toward the Sun. Some of these comets eventually pass through the inner solar system, briefly becoming visible from Earth before continuing on their long journeys back into darkness. In this way, the motion of the solar system through the galaxy may occasionally trigger waves of comet activity that last for millions of years. Yet such events unfold slowly, on timescales far longer than human history. To us, the solar system feels stable and unchanging. The planets follow predictable orbits. The Sun rises and sets with steady rhythm. The night sky appears almost timeless. But in reality, the solar system is constantly moving. At this very moment, the Sun is traveling through the galaxy at a speed of roughly 800,000 kilometers per hour. That may sound incredibly fast, yet even at that speed, the distances between stars are so enormous that the solar system drifts quietly through space without encountering other stellar systems. The nearest neighboring star system, Alpha Centauri, lies more than 4 light-years away. Between here and there stretches a vast ocean of interstellar space. Within that ocean drift faint clouds of gas, invisible magnetic fields, and tiny grains of dust. It is an environment so thin that even the best vacuum on Earth would seem dense by comparison. And yet, this sparse medium fills the entire galaxy. Occasionally, the solar system may pass through slightly denser regions of this interstellar gas. Some scientists believe that such encounters could influence the outer boundary of the heliosphere, compressing or expanding the protective bubble created by the solar wind. But these changes occur slowly and gently. For life on Earth, the effects are almost impossible to notice. From our small world orbiting the Sun, the galaxy appears as a glowing band of light stretching across the night sky. That soft, milky glow is the combined light of billions of distant stars. For ancient civilizations, the Milky Way inspired myths and stories. Many cultures imagined it as a river of light flowing across the heavens. Others believed it was a path traveled by spirits or gods. Today, modern astronomy has revealed its true nature. The Milky Way galaxy is a giant spiral galaxy. Its vast disk spans more than 100,000 light-years from one side to the other. At its center lies a supermassive black hole known as Sagittarius A star. Around that center swirl enormous spiral arms filled with stars, gas, and dust. Our solar system resides within one of the smaller spiral arms, known as the Orion Arm. It is a relatively quiet neighborhood in the galaxy, far enough from the crowded galactic center to avoid intense radiation, yet rich enough in heavy elements to form planets like Earth. In many ways, this location may have been important for the development of life. Too close to the galactic center, and frequent supernova explosions might have made life difficult. Too far from the center, and the ingredients needed to form rocky planets might have been scarce. Instead, the solar system occupies a comfortable middle ground, a calm corner of the galaxy, where stars shine gently and planets can form. As the solar system continues its journey through the Milky Way, it will slowly change position within the galaxy. Over hundreds of millions of years, the constellations visible from Earth will gradually shift. Stars that appear close together today will drift apart. New stars will rise in the night sky, while others fade away. Yet, the deeper structure of the solar system will remain the same. The sun will continue to shine. The planets will continue to orbit. And the quiet outer frontier, from the Kuiper Belt to the distant Oort cloud, will remain a frozen archive of the solar system's ancient past. These distant regions preserve the remnants of the cosmic disk from which the planets were born. They are time capsules, holding clues about the earliest days of our star system. And while spacecraft such as Voyager 1 and Voyager 2 continue drifting toward the stars, scientists here on Earth continue studying the solar system in ever greater detail. New telescopes peer deeper into space. New missions explore distant planets and moons. With every discovery, we learn more about the origins of our cosmic home. But perhaps the most remarkable thing about the solar system is this. Among all the planets orbiting the Sun, one small world developed oceans, atmosphere, and life. A world where conscious beings could look outward into the universe and begin asking questions about their place within it. That world is Earth. As we leave behind the distant frontier of the solar system and travel inward toward the warmth of the sun, the environment of space begins to change once again. The cold darkness of the outer regions slowly gives way to brighter light and stronger heat. Here, much closer to the sun, lie the rocky inner worlds of our solar system. These planets are very different from the giant gas worlds far beyond the Kuiper Belt. Instead of enormous atmospheres made of hydrogen and helium, the inner planets are solid and dense. They are built mostly from rock and metal, the heavy elements that remained close to the sun during the early formation of the solar system. 4 such planets orbit in this region. They are Mercury, Venus, Earth, and Mars. Together they form what scientists call the terrestrial planets. Each of these worlds has its own unique story, but the first 2, Mercury and Venus, are perhaps the most extreme. They are worlds shaped by intense heat, powerful geological forces, and the overwhelming influence of the Sun. Let us begin with the smallest planet in the solar system. The planet Mercury orbits closer to the Sun than any other world. From its surface, the Sun appears more than 3 times larger in the sky than it does from Earth. The sunlight is blindingly bright, and the heat during the day can reach temperatures of about 430 degrees Celsius. Yet, despite being so close to the Sun, Mercury is not always scorching hot. Unlike Earth, Mercury has almost no atmosphere. Without an atmosphere to trap heat, the planet cools rapidly after sunset. During the long Mercurian night, temperatures can plunge to nearly negative 180 degrees Celsius. This dramatic swing between extreme heat and extreme cold makes Mercury one of the most hostile environments in the solar system. Mercury is also a very small world. It is only slightly larger than Earth's moon. Its surface is covered with craters formed by billions of years of asteroid impacts. In many ways, the landscape of Mercury resembles that of the moon, a rocky, ancient terrain scarred by countless collisions from the early days of the solar system. One of the most striking features on Mercury is the enormous impact basin known as the Caloris Basin. This giant crater was formed billions of years ago when a massive asteroid slammed into the planet's surface. The impact released an unimaginable amount of energy, sending shock waves through the entire planet. Even on the opposite side of Mercury, the ground was fractured and reshaped by the force of the collision. Despite its small size, Mercury hides an interesting secret deep inside. Scientists believe the planet contains a surprisingly large iron core. This metallic core may make up more than half of the planet's total volume. In fact, proportionally speaking, Mercury's core is larger than that of any other planet in the solar system. This dense core creates a weak magnetic field around the planet. Although much smaller than Earth's magnetic field, it still interacts with the solar wind streaming outward from the Sun. For centuries, Mercury remained difficult to study. Its close proximity to the Sun made observations from Earth extremely challenging. Only in recent decades have spacecraft begun exploring this mysterious world in detail. One of the most important missions was Messenger, a spacecraft launched by NASA. After traveling for more than 6 years, Messenger entered orbit around Mercury in 2011. During its mission, it mapped the planet's surface, studied its composition, and revealed many new details about this small but fascinating world. Among its discoveries was evidence that water ice may exist in permanently shadowed craters near Mercury's poles. Even so close to the Sun, some regions of Mercury never receive direct sunlight. Inside these shadowed craters, temperatures remain cold enough for ice to survive for billions of years. It is a surprising reminder that even the most hostile environments can sometimes hide unexpected mysteries. Not far beyond Mercury's orbit lies the second planet from the Sun. This world is Venus. From Earth's perspective, Venus is one of the most beautiful objects in the night sky. It often appears as a brilliant white star, shining brightly at dawn or dusk. Because of its brightness, ancient civilizations around the world carefully observed this planet. The ancient Romans named it after their goddess of love and beauty. For centuries, people imagined Venus as a world similar to Earth. Its size is almost identical to our own planet. Its gravity is only slightly weaker. Many early astronomers wondered whether Venus might be covered in oceans or forests. But the truth turned out to be very different. Venus is not a paradise. It is one of the most extreme environments in the entire solar system. The surface of Venus is hidden beneath a thick atmosphere made mostly of carbon dioxide. This dense atmosphere traps heat through a powerful greenhouse effect. As sunlight reaches the surface, the heat becomes trapped beneath the clouds and cannot easily escape back into space. Over millions of years, this process transformed Venus into an incredibly hot world. Today, the surface temperature of Venus reaches about 465 degrees Celsius. That is hot enough to melt lead. Even more astonishing, this temperature remains nearly the same everywhere on the planet, day or night, equator or pole. The atmosphere of Venus is also extremely heavy. At the surface, the atmospheric pressure is more than 90 times greater than the pressure at sea level on Earth. Standing on Venus would feel like being deep beneath the ocean on our own planet. Above this crushing atmosphere lies a permanent layer of thick clouds. These clouds are made not of water, but of droplets of sulfuric acid. They reflect a large portion of sunlight back into space, which is why Venus appears so bright when viewed from Earth. But beneath these clouds lies a harsh and hostile landscape. Radar images from spacecraft have revealed that the surface of Venus is covered with vast volcanic plains, mountains, and giant lava flows. Volcanoes appear to have shaped much of the planet's surface. Some scientists even believe that volcanic activity may still occur there today. Unlike Earth, Venus does not appear to have plate tectonics. Instead, its surface may occasionally undergo dramatic global resurfacing events, where huge areas of crust are melted and replaced by new volcanic rock. Another unusual feature of Venus is its rotation. Most planets rotate in the same direction that they orbit the Sun, but Venus spins in the opposite direction. This means that on Venus, the Sun would rise in the west and set in the east. Even more strange is how slowly Venus rotates. A single day on Venus, one full rotation of the planet, takes about 243 Earth days. Yet Venus completes one orbit around the Sun in only 225 Earth days. In other words, a day on Venus is actually longer than a year. Exploring Venus has proven extremely difficult. The extreme heat and pressure quickly destroy most spacecraft that attempt to land on its surface. Nevertheless, several missions have succeeded in briefly touching down and sending back valuable data. Among the most successful were the Venera program landers developed by the Soviet Union during the 1970s and 1980s. These robotic explorers survived only a short time on the surface before the intense conditions destroyed them. But in those brief moments, they captured the first images ever taken from the surface of Venus. The pictures revealed a rocky landscape beneath an orange sky filled with thick haze. It was a view of a world both familiar and alien. Mercury and Venus demonstrate how dramatically planets can differ, even when they formed from the same solar nebula billions of years ago. Both worlds formed in the intense heat of the inner solar system. Both are rocky planets shaped by impacts and volcanic activity. Yet their final destinies turned out very differently. Mercury became a small, airless world scarred by ancient collisions. Venus evolved into a planet wrapped in a crushing atmosphere and locked in a runaway greenhouse effect. Their stories offer scientists important clues about how planets evolve. And they also remind us of how special our own world truly is. Because beyond Venus, orbiting slightly farther from the Sun, lies a planet that developed oceans, clouds, and life. A world where water flows across continents. A world where the atmosphere protects and nourishes living things. That world is Earth. Beyond the blazing world of Venus, at a distance where sunlight is warm but not overwhelming, another planet began to take shape billions of years ago. This planet would eventually become Earth, the only world we know where life has appeared. But in its earliest days, Earth was nothing like the peaceful blue planet we see today. Instead, it began as a violent and chaotic place, forged in the turbulent environment of the young solar system. To understand how Earth formed, we must travel back more than 4.5 billion years, to the time when the Sun itself was still young. Around the newborn Sun stretched a vast rotating disk of gas, dust, and rock, known as the solar nebula. Within this swirling disk, countless tiny particles of dust slowly began sticking together through electrostatic forces. These microscopic grains collided gently at first, forming slightly larger clumps. Over time, these clumps continued to merge. What began as grains of dust slowly became pebbles. Pebbles became rocks. Rocks became enormous boulders drifting through the young solar system. Eventually, these growing bodies reached sizes large enough for gravity to play a major role in their development. Once that happened, the process of planetary formation accelerated dramatically. These larger objects, known as planetesimals, began pulling in nearby material through their gravitational attraction. Collisions between them became more energetic. Some impacts shattered objects apart, but many others fused them together, allowing the growing bodies to become larger and larger. In the region where Earth now orbits, one such growing body gradually began to dominate its surroundings. This object would become the early Earth. But the process was far from peaceful. The early solar system was filled with countless leftover planetesimals and debris. As the young Earth grew larger, these objects continued to collide with it at tremendous speeds. Each impact released enormous amounts of energy. The heat generated by these collisions, combined with the heat produced by radioactive elements within the planet, caused the entire young Earth to melt. For a time, our planet may have existed as a vast ocean of molten rock. Scientists sometimes refer to this stage as the magma ocean phase. During this fiery era, the surface of Earth glowed red-hot beneath a sky filled with volcanic gases and swirling debris. There were no oceans, no continents, no atmosphere like the one we know today. Yet even in this violent environment, important changes were taking place inside the planet. As the molten material slowly circulated, heavier elements began sinking toward the center of the planet. Iron and nickel, among the densest materials present, gradually moved downward through the molten rock. Over time, these heavy metals gathered in the center of the planet, forming Earth's metallic core. This process is known as planetary differentiation. It separated the planet into distinct layers, a dense metal core at the center, surrounded by a thick mantle of rocky material, and eventually a thin outer crust. This layered structure would become one of the defining characteristics of Earth. The formation of the iron core had another important consequence. The movement of molten metal within the core eventually generated Earth's magnetic field. This invisible magnetic shield protects our planet from harmful charged particles streaming outward from the Sun. Without it, Earth's atmosphere might have slowly been stripped away by solar radiation, much like what may have happened to Mars. But the formation of Earth was not yet complete. During this early era, the solar system remained filled with wandering objects. Some of these bodies were enormous, almost the size of planets themselves. And one of those objects would soon collide with the young Earth in one of the most dramatic events in the history of our planet. Before that collision occurred, however, the surface of Earth continued to cool gradually. As the molten ocean of rock slowly began to solidify, the earliest crust formed across the planet's surface. At the same time, gases trapped within Earth's interior were released through massive volcanic eruptions. These gases gradually built up to form the first atmosphere. But this early atmosphere was very different from the air we breathe today. It likely consisted mainly of carbon dioxide, water vapor, methane, ammonia, and other volcanic gases. There was almost no oxygen. The sky above the early Earth would have looked hazy and thick with volcanic clouds. Lightning storms may have flashed frequently through the dense atmosphere. Meanwhile, enormous asteroids continued striking the planet. This era is sometimes called the Late Heavy Bombardment. For hundreds of millions of years, Earth and the other inner planets endured frequent impacts from leftover debris in the solar system. Each collision reshaped the young planet's surface. Yet, despite this violence, the basic structure of Earth continued to stabilize. Its core, mantle, and crust became more clearly defined. Its gravity held on to the growing atmosphere, and deep within the cooling crust, the first stable rocks began forming. These ancient rocks would eventually become the foundation of the continents. Even during these chaotic early times, the stage was being set for something remarkable. Because Earth occupied a special position within the solar system, it orbited the Sun at just the right distance for liquid water to exist on its surface. Too close to the Sun, and the heat would cause water to evaporate entirely, as may have happened on Venus. Too far away, and water would remain permanently frozen, as it does across much of Mars today. But Earth lies in what astronomers call the habitable zone. This region allows temperatures suitable for liquid water to persist over long periods of time. Water, as it turns out, would become one of the most important ingredients for the emergence of life. But before oceans could form, one final dramatic event would reshape the planet forever: a colossal collision. An impact so powerful that it would blast enormous amounts of debris into space and create the companion world that still circles Earth today, our Moon. In the early history of the solar system, the young Earth had already grown into a large, molten world orbiting the bright and powerful Sun. Its interior was slowly separating into layers. Its surface was gradually cooling, and the first primitive atmosphere was beginning to form from gases released by volcanoes. But the solar system was still a dangerous and chaotic place. Countless large objects continued drifting through the inner regions of space, remnants from the process that had built the planets themselves. Among these wandering worlds was a body roughly the size of Mars. Scientists have given this lost world a name: Theia. For millions of years, Theia traveled through the inner solar system along a path not far from Earth's orbit. At first, its motion may have been relatively stable, but over time, the gravitational influences of nearby planets slowly altered its trajectory. Eventually, the orbits of Earth and Theia intersected, and about 4.5 billion years ago, the two worlds collided. The impact was unimaginably violent. Theia struck the young Earth at an enormous speed, perhaps more than 40,000 kilometers per hour. The energy released by this collision was so immense that it would have vaporized vast quantities of rock instantly. Entire sections of Earth's outer layers were blasted into space. Theia itself was largely destroyed. For a brief moment in cosmic time, the region around Earth filled with glowing debris, molten rock, vaporized minerals, and shattered fragments of two planetary bodies. A vast disk of material formed around the wounded planet. Within this orbiting ring of debris, gravity began working once again. Fragments of rock slowly collided and merged. Over time, the swirling cloud of material gradually gathered together into a single large object. That object would become the Moon. This theory, known as the giant impact hypothesis, is the leading explanation for the Moon's origin. But the formation of the Moon did more than simply add a companion to Earth. It changed our planet in profound ways. The enormous impact likely altered Earth's rotation. Before the collision, the young Earth may have been spinning much faster than it does today. The gravitational interaction between Earth and the newly formed Moon gradually slowed this rotation over billions of years. At the same time, the Moon slowly drifted farther away from Earth. Even today, the Moon continues moving outward at a rate of about 3.8 centimeters per year. This slow separation can be measured using lasers reflected from mirrors placed on the Moon by astronauts during the Apollo program. The Moon also played a crucial role in stabilizing Earth's axial tilt. Without the Moon's gravitational influence, Earth's tilt might vary chaotically over time. Such changes could dramatically alter the planet's climate. Instead, the presence of the Moon helps keep Earth's tilt relatively stable, allowing long-term climate patterns to develop. Another important effect of the Moon is the creation of tides. The gravitational pull of the moon raises bulges in Earth's oceans. As Earth rotates, these bulges move around the planet, creating the familiar rise and fall of ocean tides. Over billions of years, tides have played an important role in shaping coastlines and mixing the oceans. Some scientists even believe that tidal environments may have helped life take its first steps from water onto land. But in the earliest days after the giant impact, Earth was still far from the calm world we know today. The collision had melted large portions of the planet's surface once again. For a time, Earth may have returned to a state similar to the magma ocean phase. Slowly, however, the surface cooled once more. Volcanic gases continued building the atmosphere. Water vapor condensed as temperatures dropped, and eventually, rain began to fall. For thousands, perhaps millions of years, rain poured onto the cooling planet. The water collected in low regions of the crust. Gradually, the first oceans began forming on the surface of Earth. These oceans would become the cradle of life. But before life could emerge, the young planet still had to survive one final chapter of intense cosmic bombardment. During this era, countless asteroids and comets continued striking the inner planets. Each impact reshaped the surface of Earth, the Moon, and neighboring worlds. Over time, however, the solar system slowly began to calm. The remaining debris from planetary formation gradually diminished. Collisions became less frequent. The young Earth, now accompanied by its moon, continued orbiting peacefully around the Sun. Its oceans deepened, its crust thickened, and beneath its atmosphere, a remarkable transformation was beginning. Within those ancient oceans, simple chemical reactions were slowly building more complex molecules. And from those molecules, something extraordinary would eventually appear. After the violent collision that created the moon, the young Earth slowly began to calm. The surface of the planet, once again melted by the enormous impact, gradually cooled over millions of years. Rivers of molten rock hardened into solid crust. Volcanoes still erupted frequently, releasing clouds of gases into the atmosphere. But the constant rain of massive impacts from the early solar system was beginning to fade. The chaotic era of planetary formation was slowly coming to an end. Above the cooling surface of Earth hung a thick and hazy atmosphere. It looked nothing like the clear blue sky we see today. Instead, the air was filled with volcanic gases, carbon dioxide, water vapor, methane, ammonia, and other compounds rising from the planet's interior. There was almost no oxygen. Lightning storms may have flashed frequently through the dark clouds of the young atmosphere. Volcanic eruptions lit the horizon with glowing rivers of lava. The surface of the planet was still unstable, with large portions of crust forming, breaking apart, and reforming as heat escaped from deep inside the Earth. Yet something remarkable was about to happen. As temperatures slowly dropped, the enormous quantities of water vapor in the atmosphere began to condense. Clouds thickened. Rain began to fall. At first, the rain may have evaporated quickly as it struck the still hot surface. But as the planet continued cooling, more and more water was able to remain on the ground. Eventually, rain fell faster than it could evaporate. Water began to collect in low regions of the planet's crust. Over thousands, perhaps millions of years, rainfall continued almost endlessly. Vast basins filled with water. The first oceans of Earth slowly appeared. Some scientists believe that much of Earth's water came directly from the gases released by volcanoes inside the planet. Others suggest that additional water may have arrived from icy asteroids and comets striking the young Earth during the final stages of planetary formation. These icy visitors from the outer solar system, perhaps originating from regions like the Kuiper Belt, may have delivered additional water molecules to the growing oceans. Whatever the exact source, the result was extraordinary. Within a few 100 million years after the planet's formation, Earth had become a world covered in water. From space, it would already have appeared as a blue planet. The presence of liquid water was crucial. Water acts as a powerful solvent, allowing chemical reactions to occur easily. Molecules can dissolve, move freely, and interact with one another. In the early oceans of Earth, countless chemical reactions were taking place every moment. Simple molecules combined to form more complex ones. Energy from lightning, volcanic heat, and ultraviolet radiation from the sun drove these reactions forward. The oceans became a vast chemical laboratory. Some scientists believe life may have first emerged in shallow tidal pools along ancient coastlines. Here, cycles of evaporation and refilling could have concentrated organic molecules, allowing them to combine into more complex structures. Other researchers suggest that life may have begun deep beneath the ocean surface. In these dark environments, cracks in the ocean floor allow seawater to seep down into the hot rock beneath the crust. The heated water then rises back through hydrothermal vents. These vents release warm, mineral-rich fluids into the surrounding ocean. Such environments provide both energy and chemical nutrients that could support early biological processes. Regardless of the exact location, at some point, more than 5 billion years ago, something extraordinary happened. Certain molecules began organizing themselves in ways that allowed them to replicate. These primitive chemical systems could make copies of themselves. They could store information. They could evolve. In that moment, chemistry crossed a profound boundary and became biology. The first life forms appeared. These earliest organisms were extremely simple, far simpler than even the smallest modern bacteria. They were likely single-celled microbes living in the oceans of the young Earth. They had no complex structures, no nervous systems, and no awareness of the universe around them. Yet they possessed one remarkable ability. They could reproduce. And with reproduction came evolution. Each generation introduced tiny variations. Some changes helped organisms survive better in their environment. Those successful traits were passed on to future generations. Over vast stretches of time, this process slowly increased the complexity of life. For billions of years, life remained microscopic. Simple organisms dominated the oceans. But even these tiny creatures gradually transformed the planet. Some early microbes developed the ability to use sunlight as an energy source through a process called photosynthesis. These organisms released oxygen as a byproduct of their metabolism. At first, the oxygen reacted with iron and other minerals in the oceans. But eventually, oxygen began accumulating in the atmosphere. This event, known as the Great Oxygenation Event, dramatically altered Earth's environment. Oxygen allowed the development of more complex forms of life. It also created the ozone layer in the upper atmosphere, which protects the planet from harmful ultraviolet radiation from the sun. Slowly, over billions of years, life continued evolving. Single cells became multicellular organisms. Simple creatures developed specialized tissues and organs. Eventually, life spread from the oceans onto land. Forests grew, animals walked across continents, and millions of years later, intelligent beings would arise who could look up at the night sky and wonder how their world began. All of this, the oceans, the atmosphere, the biosphere, traces its origins back to the early history of the solar system, to the formation of the sun, to the collisions that built the planets, to the giant impact that formed the moon. and to the delicate balance of conditions that allowed Earth to become a living world. Today, as our planet continues orbiting the Sun within the vast Milky Way galaxy, life continues its long evolutionary journey. Human beings now send spacecraft to explore the planets. We study distant stars and search for other worlds that might also harbor life. And every discovery reminds us of something profound.